So I'm Stephen Carrejero and I'm with my partner here, Macrinia Julio, and today we're going to present our thesis proposal, which is polyaniline and zeolite as an anti-corrosion coating for stainless steel substrate. So stainless steel have been widely utilized for the manufacture of products in various fields, and it is highly desired not only for its fortifying strength and luster, but also for its high corrosion resistance and low maintenance. Now, several applications of stainless steel include cookware, cutlery, surgical instruments, construction materials, and even in major industrial plants, we can see them being used as parts of the machinery or equipment for their production process. Now, stainless steel, just like any other type of metal, no matter how good its properties are, is still susceptible to corrosion attack. And that is why the main objective of our study is to devise an anti-corrosion coating using polyaniline and zeolite. So, it is common knowledge that corrosion degrades important infrastructures, especially steel-reinforced ones like steel-reinforced highways, buildings, parking lots, bridges, and even electrical towers. And when corrosion continues to act upon these structures, in time it might lead to the eventual failure or collapse of the said structure. On the other hand, for major industrial plants, the consequences of corrosion is a bit more on the economic side. Take for example, an equipment that has become corroded. What would happen is that it would lose its efficiency. And when that happens, it would affect the whole production process of the manufacturing plant, making it slower. And when that happens, the company would have to spend more money on the production process because more energy would be needed by the equipment for it to function. Then when corrosion continues to damage the equipment, there might come a time that the equipment becomes no longer serviceable. And when that happens, the company would have to account for that by having it repaired, or the worst case scenario is that they would have to have it replaced, which means that they would need to buy a new one. And we all know that industrial equipment does not come cheap, so it would cost them a lot of money. Then there's also product contamination. If the equipment has become corroded, then most likely there might be impurities on the final product of the production process. So when these products don't pass the quality control test, then the company would have no choice but to dispose of them. So they would not be able to release it out to the market, and therefore they wouldn't gain any profit from that. So you see, this study will help solve not only the ground level problems involving corrosion, but also the large scale ones, just as I've said earlier, in major industrial plants and construction businesses. So this study would make it possible by prolonging the service lives of the machinery, materials, and tools of their respective industries. And it will also prevent these industries from having to incur additional production and maintenance costs. So for the scope and limitations, so in this study, what we will do is we will take zeolite and incorporate it into the polymer matrix, which is the polyaniline. And the resulting composite material will then be electro-deposited to our metal substrate, which is stainless steel. Now, the fabrication technique that we will use for the fabrication of the polyaniline and zeolite composite will be based on a methodology of a recently published study. Now, to study the corrosion protection ability of our coating, we will prepare 3 samples. The first one would be stainless steel without any coating. The second one would be coated with pure polyaniline. And the third one would be stainless steel coated with our material, which is the polyaniline and zeolite composite. And these 3 samples will all be subjected to corrosion test. And from there, we will get their respective corrosion rates. So the protection ability of our coating will then be determined by comparing its corrosion rate versus the corrosion rate of the other 2 samples. And as per the limitations, we will only make use of one metal substrate, which is stainless steel. Secondly, we will only utilize electrochemical synthesis for the synthesis of our polymer, and we will not do the chemical route, and we will expand on that later. So we will do that due to several advantages of electrochemical synthesis over its chemical synthesis part. And lastly, for the corrosion test, this study will only utilize the potentiodynamic method and will not feature other types of corrosion tests such as EIS or electrochemical impedance spectroscopy. So moving on, corrosion is basically the formation of a thin layer of compound on the surface layer of a metal as it reacts with water and oxygen. Now this thin layer of compound is what we call an oxide layer, and the oxide layer is a metal's only natural defense against corrosion. Now the problem with oxide layer is that it is not dense enough to prevent further diffusion of the aggressive species into the metal surface. Now, the rate at which a metal corrodes is basically related to its reactivity, and some metals are more reactive than other metals. And to get a general idea about the reactivity of common metals, let us refer to this reactivity table of common metals. So, slowing down the rate of corrosion is basically hindering or preventing a metal from forming its respective oxide layers. Take for example a bicycle frame. So, if you want to coat it and if you want to protect it from corrosion, you can apply a thin coating of paint, wherein the paint would act as the barrier between the corrosive environment and the metal surface. Now, going back to the reactivity table, another thing that we can do is we can take a metal and have it coated with another metal. So for example, if you want to coat iron, then what you can do is you can choose a much more reactive metal than iron. Say for example, zinc. So the zinc would form its zinc oxide layer and would act as the sacrificial component between iron and zinc. So what would happen is that it would degrade first before the aggressive species come into contact with iron. Alternatively, you can choose a much less reactive metal such as silver, gold, and platinum, but that would be very costly and expensive and not economical. So in the past, what researchers did is they made use of hexavalent chromium coatings, but due to its carcinogenic nature, it actually poses health and environmental risks. So this is now where conducting polymers come into play. So conducting polymers, unlike your typical polymer, which is basically just insulators like rubbers and plastics, conducting polymers are special in a sense that it has both the properties of semiconductors and insulators. So in a way, you can say that conducting polymers are polymers that are able to conduct electricity. So at present, we can see them in the field of biomedical technology for controlled drug release and stimulation of nerve regeneration. We can also see them in the manufacture of supercapacitors, lithium-ion batteries, solar cells, and biosensors. Another thing is that they are being used for the manufacture of super hydrophobic surfaces, which makes them a good candidate when it comes to the fabrication of a thin protective layer for several purposes. Now, for this study, we chose a specific type of conducting polymer, which is polyaniline. Now, we chose polyaniline due to several reasons. So, the first one is because it is cheap. The second one is because it is easy to synthesize. And, of course, lastly, it has great electrical properties. So, polyaniline may exist in different forms depending on the degree by which you oxidize it. So, one of its form is the permigranulin form, which is 100% oxidized. Then we also have its leucoemeraldine form, which is 100% reduced, and it's basically an insulator. Now the third one is its emeraldine form, which is the most conductive among the other forms of polyaniline. And for this study, we will make use of its emeraldine form because, as I've said, it has the highest conductivity among the other three forms of polyaniline. And why? Because for this study, we will utilize electrochemical synthesis. And electrochemical synthesis of polymer requires that the coating material be conducting. So, there are basically two ways by which you can synthesize polyaniline. First, you have the chemical synthesis, and the second one is the electrochemical synthesis method. So, for this study, we chose to go with. So, chemical synthesis basically involves three reactants. First, you have the aniline monomer, the acid wherein you can dissolve the monomer, and the third one is an oxidant which acts as a catalyst. So the oxidant withdraws proton from the aniline monomer and allows it to bond with other aniline monomers, which in turn would form long polymeric chains which would result to your polyaniline. As for the electrochemical synthesis part, it is similar to the electroplating of metals. For our setup, we will make use of the 3 electrode setup, which has a working electrode, a reference electrode, and a counter electrode. For the reference electrode, we will make use of an AgCl reference electrode, and for the counter electrode, it's gonna be platinum, and for the working electrode, it would be the stainless steel. Wherein the polymer will be transferred to the working electrode by applying an electric current. So we chose to go the electrochemical route due to several reasons. So first of all, as opposed to chemical synthesis, this method does not require a catalyst, which means that the electrodeposited polymers are essentially pure and homogeneous. Another thing is that it allows us to have a finer control over the thickness of our coating, and it allows us also to achieve crystallinity easier. So my partner here will discuss about how polyaniline was used as an anti-corrosion coating in the past.
So polyaniline as an anti-corrosion material continuously have gained much of an interest by many researchers nowadays. So today I will be presenting a brief timeline of their studies. So in the year 2006, an author named Venkatacharya investigated the effect of polyaniline coating on stainless steel substrate at different mediums such as sulfuric acid, hydrochloric acid, and NaCl medium. Based on the results, the polyaniline coating can effectively protect the substrate in terms of hydrochloric and sulfuric acid by increasing its corrosion resistance and charge transfer resistance. On the other hand, for NaCl environment, they found out that this coating cannot effectively protect the substrate. So to further improve the polyaniline matrix, additives are used, and these additives can enhance the barrier ability and mechanical stability of our polyaniline matrix. So in the year 2014, author named Nushabali and his colleagues used Montmorillonite clay as a filler for the polyaniline matrix on stainless steel substrate. They subjected it to hydrochloric acid and investigate the anti-corrosion test. So based on the results, these nanoparticles, Montmorillonite nanoparticles, act as a barrier and can increase the diffusion pathways in which the corrosive medium is passing through, so which can cause delay to the transport of the corrosive medium. So in the year 2015, an author named Taheri and his colleagues introduced zeolite as a filler for anti-corrosion material. So they use zeolite, and for the matrix they use also polyaniline. It was electrochemically deposited on a copper substrate under galvanostatic condition, and the zeolite presence generally increases the tortuosity of the diffusion pathways. What do you mean by tortuosity? It is something related to curved path, and this curved path will generate delay in transport of the corrosive medium from the substrate. So moving on, to give you a background of our filler, zeolite are three-dimensional microporous crystalline solids with a well-defined structure that contain aluminum, silicon, and oxygen in its framework. So generally, zeolites are used by many researchers as a catalyst, ion absorption application, antibacterial application, and anti-corrosion application. So the idea zeolite as an anti-corrosion material is that zeolite are non-toxic material. It is chemically stable and mechanically stable. In terms of its microporosity, it provides a high surface area and can enhance the absorbative property of of the coating. So moving on. So to evaluate the anti-corrosion performance of our coating, we subject it to anti-corrosion testing. So the concept of anti-corrosion testing is that the coating is exposed to the coating panel is exposed to a aggressive medium wherein it is investigated by a software or a computer which evaluates the parameters such as corrosion rate and other parameters involving corrosion testing. So there are two types of corrosion testing. First one is electrochemical impedance spectroscopy or EIS. It involves it determines the long-term performance of the coating by determining its charge transfer resistance and charge transfer current. On the other hand, for the second type, the polarization method. So for the polarization method, it involves changing the potential of the working electrode and investigating the current produced as a function of time. So for the most common polarization method is used by many researchers is the potential dynamic. So for our study, we use potential dynamic polarization method because it provides some parameters such as corrosion current resistance, and the corrosion rate. So for the characterization of our coating, for the FTIR and UVVs and XRD, this method will determine the chemical composition and structure of our coating. It will also determine whether the coating is present to the stainless steel substrate. So for the surface morphology, we use scanning electron microscope, and in addition to our current study, we would like to add contact angle analysis, since one of the most common corrosive agent is water, and we would like to determine the relationship of its hydrophobicity in terms of its anti-corrosion performance. So for the materials used in our experiment, we use zeolite and aniline as a main component of our material. For the sodium oxalate, it is used as an initiator, and during electrodeposition, it will act as a barrier to prevent the dissolution of dissolution of stainless steel. So we use also DI water as a cleaning agent, and the three electrodes such as stainless steel substrate, AgCl electrode, and platinum electrode. So for the methodology part, there are 5 steps. For the first step, pretreatment of the electrodes. For the second step is the preparation of the solution. Third step is the electrode deposition. Fourth step is the characterization of the electrode deposited material. And for the last step is the corrosion testing. So for the pretreatment of the electrode, first, all of the electrode were polished with emery paper to remove all of the impurities present in the surface of the electrodes. It is later then rinsed with DI water and degreased by rubbing it to an acetone. So for the polyaniline zeolite preparation of the solution, first step is to dissolve 1% weight of zeolite into 100 milliliter of DI water for 3 hours, and it is subjected to a magnetic stirrer. So after that, we measure 0.2 mole of sodium oxalate and 0.15 mole of aniline. And after 1 hour of stirring, we add these two components, then subject it again to a magnetic stirrer for about 1 hour. So after 1 hour, we remove the solution into the magnetic stirrer and subject it to a sonicator for homogenizing the solution. So for the electrodeposition part, we follow these parameters. So for the first parameter, the volume of PZN should be 30 milliliter. The current used should be 2 milliampere and the duration usually takes 10 minutes. So we use 2 milliamperes for the current to prevent the overload of the potential stand. So after the deposition, the coated panel is then dried by subjecting it to an oven for 1 hour. So for the used electrode, it is cleaned by water and it is rinsed with the KOH. So to evaluate the the performance of our coating, we subject it to anti-corrosion testing. So generally, we fabricated 3 samples. For the first sample, it is the stainless steel alone. For the second sample, it is coated with polyaniline. For the third sample, it is coated with our material, the PZN or polyaniline zeolite solution. So for the anti-corrosion testing, our working electrode is immersed for 24 hours. The working electrode should be the coated panel. It is subjected to NaCN medium and it is connected to a computer wherein it runs a Nova software. This software will read and plot the results, such as it will plot the corrosion current or the corrosion rate of the substrate. So, thank you.
So that's it.
That's it, sir.